Hello, everyone. It's my pleasure to be supervising this work about coronal heating problem. This problem is one of the biggest mysteries in astrophysics. In the attempt of trying to solve this problem, NASA launched in 2018 a mission called the Parker Solar Probe, which aims at finding out what is actually happening in the solar corona. 3 of my students have had the curiosity to know more about coronal heating. They are about to present to us a short presentation talking about this mysterious problem and focusing on a process called magnetic reconnection, which could have an important contribution in the solar coronal heating. Okay, girls, go ahead.
I'm Ghida.
I'm Lara and
And I'm Nour Kadoura, and we're life science students at Houssam Hariri High School.
It's our pleasure to make this short presentation about the coronal heating problem, which still remains one of the most challenging problems in astrophysics. Some totally different kinds of heating mechanisms have been proposed to clarify the main sources behind coronal heating. One of these mechanisms is the magnetic reconnection process, and here we're going to present preliminary results showing that such a process could provide a considerable amount of heating for the solar corona.
Is it normal to move away from a fire and get heated more and more? Of course not, because usually it gets colder the farther you get from a heat source. Nevertheless, this is what is observed in the solar atmosphere. Instead of decreasing, the temperature increases by moving away from the solar surface, the photosphere, up to the corona, which is the outermost part of the sun's atmosphere. The temperature of the solar corona is observed to be about 300 times hotter than the sun's photosphere. This anomalous temperature observed in the solar corona gives rise to the biggest mysterious problem in solar physics, the coronal heating problem.
The top layer of the sun's atmosphere, the corona, is seen clearly from Earth during an eclipse. The first analysis of the solar corona was done in 1869 by Young and Harkness. They found that coronal particles were extremely hot. It was concluded then that a new element was discovered and they called it chromium. Later, in 1939, Grotjien showed that the hot particles found in solar corona were due to highly ionized iron, which takes place at temperature of few megakelvins. This showed that corona temperature is in megakelvins, and thus coronal heating problem began, namely how getting hotter the farther we get from a heat source.
Several mechanisms have been suggested to understand the process of coronal heating. Recently, it is widely accepted that connective motions in and below the photosphere are the ultimate sources of this heating. Because of such motions, the roots of the coronal loops, called footpoints, are displaced and either affecting the coronal magnetic field or generating waves. 2 main sets of heating mechanisms for the solar corona were proposed, which are heating by dissipation of waves and heating by magnetic reconnection process, which could be generated because of footpoint displacement.
In the previous slide, we talked about magnetic reconnection, which could be a possible heating mechanism for the solar corona. But what is the magnetic reconnection process? It's actually a physical process in which magnetic field lines are rearranged and magnetic energy is converted into heat and kinetic energy. In this figure here, we have a simple illustration about how the process occurs. The downward magnetic field line 1'1 disconnects and reconnects to the upward magnetic field line 2'. Moreover, in the right figure, we did a simulation showing the magnetic reconnection process in a clear way. Initially, the magnetic field lines are anti-parallel, but once magnetic reconnection process takes place, the magnetic field lines are rearranged, similar to what we have in the illustration.
Magnetic reconnection is a fundamental process in space physics. It is believed to be behind the evolution of solar flares. As given in figure 1, this is how solar flare looks like. Magnetic reconnection is also believed to be the source of coronal mass injection, which is shown in figure 2 here. By the way, this is a real image of coronal mass ejection recorded by NASA's Stereo-A spacecraft in the meaning of August 18, 2010. Magnetic reconnection is also expected to occur in the interaction between solar wind and Earth magnetosphere. In this yellow box here in figure 3, such a reconnection due to solar wind is recently observed by the MOS mission launched by NASA on March 2015.
Now comes the main contribution of this work. Since the coronal magnetic field lines originate in the sun's photosphere at the foot points, so any motion of these foot points enforces the coronal magnetic field lines to change their topology via magnetic reconnection process. Once magnetic reconnection occurs, magnetic energy is released and thus converted into heat. Therefore, in this work, we investigate the contribution of the magnetic reconnection process in the solar coronal heating.
The problem of solar coronal heating is cumbersome and still remains one of the most unresolved problems in astrophysics. For this reason, and for better understanding, the solar atmosphere high-resolution observations should be done. This is why NASA launched on August 2018 a mission called Parker Solar Probe. This probe will fly within 6 million kilometers from the sun's surface. It will spend a total of 30 hours within the solar atmosphere. It can thus gather information about who's going in the solar corona, and it will hopefully tell us why the corona is so hot.
In this work, we performed a real simulation of a portion of a coronal region in which we have two coronal loops exhibiting two anti-parallel magnetic field lines. This simulation box has a length of 4 millimeters in the y direction and a width of 1 millimeter in the x direction. We started our simulation by assuming that the initial values of pressure, density, and temperature are all constant of time 0. And since we are dealing with corona, which is an open region, we used open boundary conditions of all sides of our simulation domain.
In this slide, we now show some of the preliminary results we got from our simulation. This left figure here gives us insight about what is actually happening to the magnetic field lines during magnetic reconnection process. Once magnetic reconnection occurs, left field lines start interconnecting with the right field lines and vice versa. The right figure here shows us the time evolution of temperature during the magnetic reconnection process. Initially, we start with a uniform temperature around this value, 8 times 10 to the power 5 kelvins, and later, at time 125 seconds, high temperature values are concentrated in the middle of our simulation box along the y direction. As magnetic reconnection proceeds, a slingshot is observed in which the temperature is continuously increasing. At the end of the magnetic reconnection process, we notice that the temperature attains 1.24 megakelvins, which is consistent with the temperature observed in the solar corona.
Here, we plot the time variation of the two averaged quantities throughout our simulation box, the magnetic and the heat energy per unit mass. Starting from its initial value, about 4 times 10 to the power 10 joules per kilometer, magnetic energy always decreases. On the other hand, the heat energy increases from 0, and it reaches a value at the end very close to that of the magnetic energy at time 0. This certainly indicates that the magnetic energy is persistently converted into heat energy. Therefore, magnetic reconnection process contributes significantly in the solar coronal heating by converting magnetic energy into heat.
What we have found in this work is that despite great advances in modeling and observation, the problem of solar coronal heating still remains one of the most challenging problems in astrophysics. Based on our results, whether it supplies the majority of coronal heating or not, magnetic reconnection is clearly generating heat in the solar corona at the same rate. Finally, we believe that this work is extremely important because it shows that the heating of the solar corona is significantly enhanced by the magnetic reconnection process.
At the end of this presentation, we would like to thank our school director, Mrs. Mona Majzoub, our high school division director, Mrs. Jana Abu Aram, our physics teacher, Mr. Mustafa Hamoud, and of course, the committee of this BAU competition. Thank you.
Okay, girls, thank you for this nice presentation.